All right, so we are continuing the discussion on shear design of reinforced concrete. We'll continue this module 6. And now, in this part of the video, we are going to talk about what are the IS 456 provisions for shear design. And then we will also discuss some design examples. Right. So we are following this IS 456 provisions for shear, and you know that IS 456 2000 is the code of practice for plain and reinforced concrete design in India. And so the expected learning outcomes from this part of the video is students should be able to identify the critical sections for shear for the design of RC members, and should we explain what is nominal shear stress and how to calculate nominal shear stress for beams with varying depth. uh, you may encounter a situation where the depth would be varying, and then how to consider that, and then the code provisions that exist in IS 456 for design of shear. Right. So first, let's talk about the critical sections for shear. Right. So before we do that, I think structural analysis is very important. We need to accurately should be able to calculate the variations of bending moment and shear force diagrams, right, for an element. Once we do that, now what is the section that we need to take for design? Now, for demand, the code says that three scenarios that the code is saying. For the case one, let's say for if you have uniformly distributed load, but then you can take critical section where you calculate your shear demand VU. Okay, VU can be at a distance d from the face of the support. So this is your face of the support, your column. For example, here the beam is resting on some kind of a pedestal or kind of a bearing. So you can see the distance is basically from D from the face of the support. Okay, so that is the critical section where you are supposed to calculate your shear demand that you are going to use in your design, right? However, if you are having a heavy load within a distance of D from the face of the column, where you are having some heavy load, some point load, for some reasons it is coming. In that case, you have to consider the section only at the face of the uh, support, not at a distance d from the face of the support. You have to consider critical section at the face of the support. For example, you have scenario two things. Okay, in this left side you have a heavy load, right side you have uniformly distributed load. So right side for shear demand you can take at a distance of d from the face of the support. Okay, but however, because you are having a heavy load that is within the distance of two times the effective depth from the face of the column, you have to consider the critical shear section as the face of the support. So you're going to overestimate the little bit conservatively estimate the shear demand. Okay. Now you can ask me, why is it the code is asking you to calculate the shear demand at a distance d from the face of the support, not at the face of the support for usual scenario, right? So there is going to be an axial thrust that is going to be coming from the support that is not going to allow the crack to form here. It is always the crack will form at a distance away from here like this. So it will not crack will not form because there is an axial thrust that is going to limit the crack formation in this region. It is going to push the crack away at a distance of d by 2 or so. So that is the reason the code is saying that you can anyway the crack is not going to form there. So you can take a distance of d for your estimation of your shear demand. So it is considering the beneficial effect of your axial thrust that is coming from your support. Okay, but we cannot consider this beneficial effort if you have a heavy load that is coming within the distance 2d from the uh, uh, face of the column. Then you have to calculate your shear demand only at the face of the support. Right. So this is also another scenario when you have a suspender beams like this. Again, like this kind of a cantilever kind of suspension that is there, then in that case also your shear demand has to be taken at the face of the support like this. Okay, not at a distance d from the support. Okay, so when beams are getting hanged from another element, again you will not have this beneficial effect. So you have to take at a distance of phase of the support for shear demand calculations. So this is very important provision that we need to consider. Now, we talked about how to calculate the shear stress, right? So T tau for elastic case is going to be VQ by IB. But we know that reinforced concrete is neither elastic nor plastic. It is inelastic. And we are also going to have a lot of reinforcement, longitudinal bar stirrups. And then, so you're going to have some kind of redistribution of stresses. The code is saying that, okay, don't worry about what is the exact shear distribution. You calculate nominal shear stress in an average sense. If you know the shear demand, you divide by breadth and depth of your effective depth of your member, then you get your nominal shear stress. Okay. Now, code also recognizes that if you are having beams of varying depth, that means you're not having a constant cross section, you are having a varying cross section, then there is going to be an additional component where either it will amplify the shear or it is going to reduce your shear demand depending upon how the beam is varying. That the code is recognizing that as this Vu plus or minus mu by d times tan beta by b. That way we have to calculate. So as your nominal shear stress. This is for uniform depth, this is for varying depth. Now we will understand what happens, why this additional component is coming when you have a beam of varying depth. Okay, so usually we consider plus when your moment demand is increasing in the same direction as the effective depth is increasing. So what does that mean? So for example, if you look at it here, let's say that I have a beam like this. Okay. Now what would be the bending moment diagram? So if you look, so we know that the bending moment diagram is going to be like this with PL by 4, right? Now for this beam, if I'm providing a cross section like this, which is less cross section for a simply supported case, and then it is going to vary like this. Okay, so here this is your beam depth. Okay, so wherever moment is higher, I'm going to put more depth. So in other words, the depth is increasing in the direction of your bending. Okay, in that case, you are going to take negative sign, or in other words, the shear demand is going to be Pu minus mu by d times tan beta. Now we will understand how this component comes in the next slide. But if your depth is increasing in the direction of your bending moment, then the shear demand, this is your Pu net shear. Okay, this is the one that we are going to use in our calculations. Okay, if d is increasing and let's say if I put it this way, if d is increasing and moment is decreasing, then your shear demand will become Vu plus mu by d into tan beta. So in this scenario is exactly opposite. So for example, for some reasons, if my beam depth, if you're not providing this way, I'm providing the opposite way. Opposite way is what? Basically, I'm having more depth here, and due to some reasons, okay. So and then I am providing like this, okay, a varying cross section. Then you can see here, now this is my beam depth, okay, for some reasons, okay. So in that case, your depth is increasing wherever the bending moment is decreasing, in the direction where the bending moment is decreasing. So sometimes we will have this kind of scenarios in some structural elements, which we will talk about. So in that case, your net shear has to be increased. So that is what we're going to have. Now, what is the uh, let me erase this. Okay, so mu will become bending moment at the section, and beta is basically angle between the top and bottom edges of the beam. So, for example, let's say bottom and top edges. So, what is the angle? So, let's say you have like this scenario. Your beta is basically this. Your beta. Okay. So, top and bottom edges of the beam. Okay. Now let us see how this thing is going. So for example, I am taking a how to adjust the shear demand. Okay, and for example, in this case, let's say I'm taking a beam where the bending moment is going like this, and then it is going like this. And shear force diagram is also like this because some load is coming here, so it is going to come down. Okay, shear force diagram is this. Now you see here, if I take this case, the first case, I am considering depth is increasing now. If I'm taking a section here at a distance, let's say at a distance of x, my bending moment is mu and shear is vu. And then if I look at the free body, if I'm providing a beam cross section like this, where with the depth like this, and then it is increasing. So you can see that bending moment is increasing in this direction. My depth is also increasing. So d is also increasing. So this is the same direction. In that case, if you look at for this particular scenario, if you look at the free body diagram, now you are having bending moment of mu that has to be resisted by internal forces. The internal forces, concrete contribution will come from Cu, and your tension force. Now what you learn, you have a beam of varying depth. So your reinforcement is going to follow the depth so that you can maximize the tension force, right? So it is going to be not straight, it is going to be at an angle. So now this moment couple is going to be given by this Tu to resist because for the applied moment, right? Then your component of this along the bar is basically going to be Tu by tan beta. Now this vertical component is going to be Tu tan beta. So if this angle is all beta, and if your diagonal component is Tu by tan beta, your vertical component is going to be Tu tan beta. Now you see here, this is an additional vertical component force that is there. Now if you look at for vertical force equilibrium, shear demand Vu should be equal to, if I call this as Tu tan beta, so basically it is going to be now acting down, right? So it's going to be Vu net plus Tu tan beta, right? So we are interested in calculating what is the net shear that is acting at the cross section where we are designing. So Vu net will become Vu minus Tu tan beta. Okay, so this is from your sigma Fy equal to 0. So vertical force equilibrium, right? Now, how is this? This is the tension force. We know that teams are usually provided reinforcements in the order of 1.5, 2%. If your demand is less, or even when you go for doubly reinforced section, you are ensuring that you're going to have tension bars are going to be yielding. Okay, that is what we discussed in your moment curvature analysis and your flexure design, right? So if you see here, the neutral axis depth at ultimate, if you are providing less reinforcement, the neutral axis depth at ultimate is going to be very small, right? So what we can say here is, then how is the moment resistance is going to come? We know that it is going to be tension force multiplied by lever. If my lever arm, I need to find what is the value for lever arm. Okay, so if you know this cross section, right? Let's say I have some steel here, right? What we are saying is, we know from your force diagram, let's say this is your strain distribution that what I have. Let's say this is epsilon c equal to 0.003 that what we did. So your neutral axis depth that is required to satisfy equilibrium will be usually very low at ultimate, right? So we have found. So then when you calculate your CC force, concrete force in compression, and then tension force in steel, we find that this distance is going to be 0.42 XU as per your IS code, right? So this is going to be XU itself is very small. So this 0.42 XU will be even less. So you can say that this distance is actually D, and this is your lever arm, and the lever arm is going to be nearly equal to that of your effective depth for a under reinforced section. And when your reinforcement levels are limited, this is an approximation that we are making. So the lever arm will be nearly equal to that of your effective depth. So that is the reason. Now, how to calculate my tension force? I know the moment. What is it? So lever arm is Now I've equated that to be effective depth. So what is tension force? Tension force is mu divided by effective depth. Okay. So that is what we have taken here, where compression force should be equal to tension force, which is mu by z, which is approximated to mu by d, because we are dealing with an under reinforced section, because code permits us to design only an under reinforced section. So we want to make sure the steel is going to yield. So when steel is yielding, both for singly reinforced as well as doubly reinforced section, your neutral axis depth is going to be very small. So your lever arm will be very close to that of your effective depth. So if you substitute that, then your net shear is going to be Vu minus mu by d times tan beta. Okay. So if my depth of the beam is increasing in the direction of my bending moment, there is a vertical component that is going to reduce the shear demand, and that value is going to be basically mu by d tan beta. Okay, you can also have, so for example, in footings you can have this situation, and there are many other situations you may encounter this situation. But if your depth is reducing in the direction of bending moment increase, which is also not correct, because we want to maximize the lever arm, but for some reasons if you end up that kind of a situation, then you have to account for that increase in your shear demand. Okay, so that is what we are going to see in the next case. So let me erase this. All right, so let's look at the next case. So again, see, now if you see here, if you look at the free body diagram of the next case, I am saying that my net shear is like this, and compression force is like this, and then you have this. Then the tension force is going to be like this. Now you will have a component, this vertical component, same Tu by tan beta will have a vertical component, which is Tu tan beta. Now that is acting opposite direction, okay, because the force is going up, so the vertical component is going to be upward, not downward. So then again, if you look at your sigma Fy equal to 0, then you will have basically net shear, let's say this is Vu, okay, so Vu will be equal to acting up, will be equal to Vu net minus Tu tan beta. Okay, so our Vu net will become Vu plus Tu tan beta. Again, Tu can be calculated as or approximated as mu by d. So this scenario again we have to take into consideration when your depth is reducing in the direction bending moment is increasing. When you have this kind of a scenario, your shear demand has to be increased by a value mu by d into tan beta. Okay, right. Now let's say that we have looked at the behavior of shear, right? From our circle, for a generalized stress state, we can convert them into principal. Generalized stress state can be converted into principal compression and tension, and then principal tension, if it is less than tensile strength of the concrete, then it's not going to have crack. But usually, if concrete is weak in, generally concrete is weak in tension, so you will exceed the tensile strength, you will have some cracks. And reinforced concrete, you are allowed to have crack. Only what we are making sure that the crack widths are limited by putting enough amount of reinforcement. Now, if you see here, the code is giving you tau c value, which is the shear strength of concrete. Again, tau c or VC is lumped as three things that we talked about in the previous set. VCZ, which is uncracked concrete contribution, vertical component of your aggregate interlock, plus the dowel action. See, all these three things are lumped together and given as a simplified expression as a tau c or your VC. When tau c is multiplied by B and D, you get your shear capacity, concrete capacity, which is VC. Now let us look at this. You can see here what we are having is 100 AS by BD, which is nothing but your PT. Okay, percentage of tension steel, and the table is given with increase in concrete grade. Okay, and then when your percentage of steel is increasing, let's see for two scenarios. Let's take M20. For M20, as you can see, for a percentage steel of 0.15, very low percentage, your tau c is 0.28. When the percentage of steel becomes 3%, then it becomes 0.82, right? So 0.28 has increased. So you can see that for a particular grade of concrete, the more and more steel that I'm providing, I am going to have higher tau c. Okay, why is it? Again, if I put at ultimate, if I put more steel, what will happen? Your neutral axis, from flexure point of view, neutral axis depth is also going to be larger, and your tensile shear strength is also going to increase with increase in your percentage of your steel, right? So this AS is basically the area of the longitudinal tension reinforcement, which continues at least one effective depth beyond the section where you are doing calculations. And at support, where the full area of tension may be used, provided the detailing, we have to make sure that the detailing of this tension steel or the steel is properly anchored as per the provisions given here in 26.22 and 26.23. Then only you can take the entire area of steel. If the steel is not anchored, only the area of steel that is anchored has to be included in this calculation. That's what it is shown here at the support section, right? So now let's look at it here for a particular percentage of steel. Now you can see here that when the grade of concrete is increasing, again tau c is increasing. Okay, why is it? Because higher the grade of concrete, higher will be the tensile strength, and shear strength is always a function of your tensile strength. So higher the concrete compressive strength, higher the shear strength, so tau c is increasing. Similarly, for a particular grade, higher the amount of tension steel, higher your tau c. The reason is, again, you are going to have, again, the percentage of steel also going to help you in giving more dowel resistance, and you are also going to have end up with more uncracked concrete in compression. So these are the two reasons why with increase in your steel, your tau c is increasing. But it's not like increasing all the time. So you see here 0.28 to 0.7 to 0.81 it is increasing. After that it is remaining more or less same. So it's not like you put more and more tension steel, you will keep on getting increasing torsion because there is a maximum limit to it, right? The double action as well as for uncracked concrete contribution, there's going to be a maximum limit. That's what the code is recognizing because you may end up failing in other modes like over reinforced or a compression control mode. That is why the code is saying that the beneficial effect of increasing your tau c is limited to certain value. Right. So these are the values that we are going to get. Now this is for beams. Okay. So this is what we have. If you look at it at 1.5 percentage of steel, again you can see that as the grade of concrete is increasing, your tau c is increasing because predominantly because tensile strength of the concrete is also increasing. Now again for a particular grade of concrete, you can see here as the percentage of steel is increasing, your tau c is increasing, but up to a certain level, after 2% or so, it remains, the increase is not significant. It's more or less plateaus. Okay, because when you put a lot of steel on the tension side, you may end up with other failure modes which code doesn't want you to have. Now, so this is the expression. So whatever the value that are given in the table is uh, can be expressed in this form of equation. As you can see, the square root of, whenever you see square root of FCK, it is basically a some form of tensile strength of concrete, and shear strength is always linked to the tensile strength of concrete. So that is why here. So higher the grade of concrete, higher will be the shear strength. And then in addition to that, you also have a factor called beta, which is function of your amount of your tension steel. Again, beta is coming in both the numerator and denominator, but higher the amount of PT, then you'll have higher tau c, like what we have included. So the magnitude of design shear strength, concrete shear strength, depends upon the grade of concrete and the percentage of tension steel. So these are the two important parameters that are going to govern your concrete shear strength. And average shear stress, we know what is the shear force divided by the area of the cross section, or it is nothing but your BD. Basically, tau V, nominal shear stress, basically VU divided by B times D. And in B, we have to take breadth of the web. Let's say if you're doing a flanger section, then the B you have to take web, because web is the one that is going to take predominantly the shear load. Now, this is for beams. Now, let's say for slabs, what happens? Okay, so slabs, the code is saying that for solid slab, the design shear strength, whatever that was discussed before, has to be multiplied by K. Now, what is the value of K? For example, if the slab is getting lesser depth, okay, as the depth of a slab is increasing, you see here the K factor is increasing, okay, as the slab gets thinner and thinner, then your amplification in your shear strength is recognized. Now, why is that? As the depth is increasing, your transverse shear stress is actually going to reduce and K factor is expected to increase. The code recognizes this fact. In addition to that, for also when the slab becomes thinner and thinner, in addition to the bending action, you are also going to get more of, you'll transfer the load more through your membrane action. That is by stretching. So that is also one of the reasons the code is recognizing that when you provide thin slab, you are expected to have higher shear strength. That is why that K factor. When you are putting slab of less than 150 mm or less, whatever tau c that you are calculating, you can multiply this by 1.3. That means I am getting 30% higher shear strength when your thickness of the slab is less. Again, when your depth of the slab is 300 or more, the code is limiting K to 1. Okay, so then your transverse shear stresses will increase and then you don't get that beneficial effect of your membrane action. In addition to that, again, the tau C that what we have discussed, it does not include any beneficial effects of your uh, axial compression. So the code also recognizes that whenever you have members subjected to bending, shear, and axial compression, and you can easily see that from two sheets of paper that what we are having. Okay, so if we have these two sheets of paper, when you slide against each other, and when you hold it, you cannot slide this paper against each other. So the presence of axial compression is going to help in improving your shear strength. That can be explained from your Mohr circle also. When you have axial compression, basically Mohr circle will shift more towards compression side, or in other words, your principal tensile stresses will be reduced for a constant value of shear. Okay, so the presence of axial compression, that is what we do it in pre-stress also. When you put element under pre-stress, it takes more load for it to crack in tension. So the code recognizes this. The code is saying that, okay, whenever you have axial compression, that I have to include that effect, beneficial effect, in the form of some simple equation where it is saying that you can increase that tau c by a factor called delta, which is 1 plus 3 pu by agfck or 1.5, whichever is less. So let's say I get 1.6 here and here it's 1.5, then the delta has to be limited to 1.5. Okay, or if I'm taking, let's say this is 1.3 and this is 1.5, then I have to use only 1.3. Now Pu is axial compression and Ag is your gross area and Fck is your characteristic compressive strength of concrete. Okay, right? There is also another reason the code is saying your shear stress, the tau b, the nominal shear stress, can never be more than tau c max. The reason is again the shear, an element with a generalized stress state. If you draw the Mohr circle, you will get principal compression and principal tension. Now we have said this sigma 1 can also reach your compressive strength F prime C if you are not careful. But most of the time, what will happen? The sigma 2, which is a principal tension, will reach your tensile strength. But it is not necessarily all the time true. If you are having a very thin member, and especially for a pre-stress member with a lot of pre-stress, you may end up with a situation that principal compression stress can reach the value of a compressive strength of concrete and it can lead to crushing. Or, in other words, if your shear demand is very high and if you are providing very less area, then you may end up with a situation that your principal compressive stress may reach the compressive strength of concrete and it can lead to crushing. The code is preventing us from designing such sections so that tau v can never be more than tau c max. If your nominal shear that what you're calculating, if it is going to be greater than your maximum shear stress that is allowed for a particular grade of concrete, then what we have to do is we have to increase the dimensions of the section so that tau v is always limited to tau c max. Yeah, yeah, I'm in a class, right? So you see, the code is also giving different values for your tau c max as a function of your grade of concrete. Okay, so you can see here. For M30, I'm getting M3.5, M35, 3.7, and M40 and above, it is limited to 4 megapascal. So tau V can never exceed tau C max that is given here. The reason is your principal compression stress cannot exceed compressive strength of concrete. In fact, we know that when concrete fails in compression, it's a very, very brittle mode of failure. And shear, when it is failing in shear compression, it's again a very brittle mode. Shear itself is a brittle mode, even when it is failing in tension. Now, when the shear is failing in compression mode, it is even more brittle. It will not give you any warning. So the code is prohibiting you from designing such sections by making sure that tau v has to be always less than tau z. Okay. So this is what we have said. So this can lead to this kind of a scenario, right? So now let's see what are the different types of reinforcement that we have. The code allows use of three types of shear reinforcement. We can put vertical stirrups. Vertical stirrups are commonly used because the direction of shear stress can change, especially when you have a lateral loads or wind load or earthquake load. The direction of shear stress can change. So you cannot always put reinforcement perpendicular to the crack. So the practical thing is to put reinforcement vertically so that the crack direction when it is changes also the vertical reinforcement is going to be very effective. Or if you are very sure of the shear direction, then you can also put inclined stirrups, but it's not actually recommended. Only for gravity loads. If you're not very sure, if you're sure, you can put. But the most common thing is to put vertical clips. In the olden days, people also used to do this bent up bars. Okay, for example, the sagging or the bottom reinforcement, if it is no longer required, if you have a simply supported condition, for example, this can be bent up. But that's in the modern day construction, we don't really use this because it's going to take a lot of time to bend up. So what people do is basically they cut it and then they put two layers of steel. Right now, let's see for a cracked beam, what is the contribution of your stirrup. Now, for example, let's say that you're estimating a shear demand and now we've estimated your shear capacity. If your VU is more than BC, that means the shear demand is higher than your concrete capacity in uh, the shear capacity, then what we have to do is whatever the difference is there. So VU minus VC, that is the additional thing resistance I need to provide in the form of stirrups. Okay, so this is your contribution for stirrup that whatever that you're providing should be higher than whatever the shear demand minus the concrete capacity in shear. So now concrete capacity in shear we can calculate from tau c, right? Now let's take a case for a generic case of a inclined stirrup like this, which are spaced at a distance of s. Okay. Now I am assuming that with respect to horizontal, these stirrups are making an angle alpha. And also we know that in shear, you're going to have a 45-degree crack right at the middle. And if I assume this crack angle to be an average since 45 degree, right, then you can see that this is your effective depth. Okay, this is your depth. So we can say that this crack, if I assume 45 degree, this distance is going to be basically d cot 45, which is equal to d. And then if I take this alpha and if it is this, let's say one stirrup is ending at the edge of this crack, then if I continue that until that stirrup, then this distance is going to be d cot alpha. Okay, this is because this is again d and this is alpha, so this distance is going to be d cot alpha. So the entire distance, that is the stirrups which are within this distance of S1, that is d cot 45 plus d cot alpha, will be intercepted by this crack. Okay, so now the stirrups basically the shear is going to put the stirrup in tension. Now, what would be the vertical component? So now let's see how many stirrups are that getting crossed. So if I know the spacing, number of stirrups that are crossing the crack will be S1 by S. Now what is S1? Basically it is D cot 45 plus cot alpha. Okay. divided by S. Okay, so that is this. This is the number of stirrups. Now, what is the maximum force that stirrup can offer? 0.87 Fy times its area. Let's say area of stirrups is ASV. Now, this is stirrup is now at an angle alpha. Now, what is that it is going to resist? The vertical component of this tension force is going to resist the shear. So, the vertical component is basically 0.87 F by ASV times sin alpha. Now, ASV stands for area of stirrup legs that are resisting shear. In fact, the shear crack will be a through crack. If I am having a crack, if I have multiple number of legs, all of them will resist the shear. So, usually what we put is 2 leg or sometimes 3 leg, and we can have multiple legs stirrups also as well. So when you have multiple number of legs, all of them will be resisting that crack. So depending upon the number of legs that what we are having, ASV will be equal to 2 times area of your one stirrup. Okay, so if I have 3, then area of ASV will be area of one stirrup. Let's say stirrup. Right? So this is the vertical component. So this is the way we define. So this is the maximum that when it is yielding is the maximum tension force it can take. That if I take vertical component sine alpha, and this will be the number of stirrup that are cutting that crack. So in this way we can find a generic expression for an inclined stirrup. Now when I keep this alpha as 90°, then we know that sin alpha will become 1, then the stirrup contribution will become 0.87 Fy ASV times B by S. This is nothing but your number of stirrups that are intercepted by this 45° crack. Okay, so this is the way we can calculate your shear resistance from stirrup. And let me erase this. So again, reiterating, stirrups will be required when your shear demand becomes more than concrete capacity, and that is the amount that we have to provide. And if you take this generic case, VUS will be TS sin alpha. The maximum tension force offered by the stirrup will be number of legs of the stirrups that are intercept multiplied by the tension force. Now this TS sin alpha I have to put. Okay, so this vertical component is only resistance shear. So if you simplify that, you end up with this VUS equation. Now, so what is the procedure for designing according to IS code? So we calculate your shear demand. The resistance that should be provided should be greater than your shear demand, just like what we did in flexion. Moment resistance has to be greater than your moment demand. And VUR is your nominal shear strength, and we use your backload shear force at the section. Now, how do we calculate your shear resistance? It is summation of your concrete capacity plus capacity of the stirrup. Now, we know that we can write that as tau C times BD, and VS is, we know that it is basically 0.87 Fy times ASV times D by SV, right? So this is basically your number of stirrups. Okay, so in this way we can calculate. Now code also recognizes that if you see that DC has 3 components: uncracked concrete, aggregate interlock, double action. That all will be activated only if your crack width is limited. Now to limit the crack width, you have to make sure that you put some minimum reinforcement. Especially when your tau V, the nominal shear stress, becomes less than tau C interval, the minimum shear reinforcement shall be provided. Though it is less than your concrete capacity, it's better to provide some nominal reinforcement. So that amount of nominal reinforcement is given as ASV by BSV should be greater than 0.4 by 0.87 Fy. Okay, so now what is ASV? The total cross section area of stirrup legs. This is what I said. So if I am having, let's say, 10 mm stirrup, and if I'm putting 2 legs, okay, so I have to multiply 2 times area of this 10 mm legs. Okay, so that is what we have to take. So area of, let's say, each leg. Okay. So depending upon what diameter that you're going to put, each area of the leg you can calculate from pi by 4 d square, and then use that in your calculations. And Fy will be your characteristic. This is again another thing that we need to take into account. Though you may use 500 grade, in your calculations, the yield strength value that you are going to use in your shear capacity has to be limited to 415 megapascal. Even if I'm using 500 grade, I have to limit it to 415. And again, the reason is Ford wants to be conservative and make sure that you are providing stirrup reinforcement at a closer spacing, because from a seismic design point of view also, providing closer types, especially in the beam column joint regions, is going to provide a lot of ductility. Similarly, in the columns also, the code recognizes that. That's why code is making sure that you are not going to provide stirrups at a larger spacing. So FY is actually limited to 415 megapascal. Now, so we can have situations when tau v becomes more than tau c, as calculated in table 9. We need to provide shear reinforcements either in the form of vertical stirrups or a bent up stirrup or inclined stirrup. One most common one is this. This is the common way we provide, because stress reversals we don't know. Right? So when bent up bars are provided, their contribution towards shear resistance cannot be more than half that of what you get for your total shear reinforcement. So again, the bent up bar contribution is not going to be very efficient. So that is the reason code is limiting that to half, not more than half that of your contribution from your total reinforcements. And now, what the stirrup contribution should be? It should be basically VU minus tau c into BD. And VUS, we have already derived that. For vertical stirrups, it is going to be 0.8785 ASV multiplied by D by SV. And for inclined stirrup, this is a generic formula. Okay, if you know the alpha of that inclined stirrup, then you can plug in and you can calculate your shear contribution of your inclined stirrup. Again, so this is a for single bar or a group of parallel bars, bent up bars. Again, this is the stirrup contributions for shear resistance. Okay, so but this again said, bent up bars are not commonly used in the modern day construction, so we don't really go for that. So, so when more than one type of shear reinforcement is used to reinforce the same portion of the beam, the total shear resistance should be computed as sum of the resistance for various types. Let's say I'm putting bent up bar, I'm putting vertical stirrup, I'm putting inclined stirrups. You calculate each one of them individually and add all of them. So that is your total resistance, with the condition that, right? So bent up bars contributions cannot be more than 50% of the total contribution. So code is limiting you to use also bent up bar contribution. And minimum spacing, again, spacing of the stirrups has to be uh, for vertical stirrups, maximum spacing cannot move more than 0.75 times your effective depth, and D for inclined stirrups at 45 degree or 300 mm. So this on all the three, whichever is smaller, we have to use that as a maximum spacing. So again, why we put this maximum spacing requirement? Because inclined crack, when you have an inclined crack forming, still I should be able to generate resistance to aggregate interlock, double action, and your uncracked concrete. When your crack pit becomes wider, then all these contributions will not be effective. So only the stirrup will be effective in resistance shear. So if you want to be a good design, if you are putting closer stirrups, then you can limit your crack width, shear crack width. Then you can realize the all the other contributions. Okay, so what is the procedure for design of shear? First, we calculate your shear force diagram and establish the critical section for shear. And then we calculate concrete capacity, which is your VC. And we also need to make sure that tau V has to be less than tau C max. This is to make sure that concrete doesn't fail in shear compression, right? So we don't want to have concrete failing in shear compression. Again, when you have a compression failure, it's going to be a very brittle mode of failure. You don't want that. So if this condition is not satisfied, the concrete dimensions has to be satisfied. Okay, right. So then first, for next step is to classify the shearing force on the beam. Let's say if your shear demand is only less than 50% of concrete capacity. So then code is saying that everything is going to remain elastic. You don't really need shear reinforcement. But I would say it's a good practice to put some nominal stirrup, even if your shear demand is less. When your shear demand is between VC and 0.5 VC, that means it has exceeded 0.5 VC, but it is less than VC. Then code is saying that you provide minimum shear reinforcement as per this provision that we discussed, and also the spacing has to be less than this. Okay. Now, when shear demand becomes more than VC, definitely we need stirrups or vertical stirrup reinforcements or shear reinforcement that we can calculate this using this thing. So this, we use this basically difference between the shear demand and concrete capacity. And then from the formula that what we have discussed, we can calculate your spacing of your stirrup. And again, most important thing is the maximum spacing has to be limited to 0.75 times the effective depth or 300 mm. So the stirrup, when you're putting for augmenting your shear capacity, spacing has to be limited to either less than 0.7 times D or 300 mm, whichever is lesser. Right. So if we summarize whatever that we have discussed in this part of the video, we looked at what are the types of shear reinforcement, what is a nominal shear, and what are the critical section that we need to consider for shear. And we also looked at when you have a beam of varying depth, there are some additional components of shear that we have to include. Either you can reduce the shear demand or you can increase the shear demand that we have to appropriately consider. And we discussed the IS4 provisions for shear, and also we discussed how to design for a particular shear demand. Right. So these are some of the references that we have used to put this material together. And thank you again. Some of the slides were prepared by one of the PhD student. I would like to thank his help.